is the most important one, so I stopped and started anew. The first and second one wouldn't show up on the AP test. The third one does. And so I'm going to try to relate this to circular motion because Newton really applied to this, and this is the first. This p squared is proportional to a cubed, or p squared equals k times a cubed. This is the original equation of motion. Nothing precedes this. This is the first equation of motion. So I'm going to start with circular motion. And I'm going to say that I have a very massive object, M. And I'm going to say that M is much, much more massive than little m. And I'm going to say that little m is in circular motion around big M. And I'm going to call this distance R. So that's going to be the distance between the centers of them. All right, so for this M here, there is one force on it. That would be the force of gravity. And it would be directing it towards the center. I would designate this as F with a big G. It's in uniform circular motion, so I would say that F net is equal to mv squared over r. And so this force that's pulling it in there is what's keeping it in this orbit, and that's equal to big G, little m, big M over r squared. And this is equal to mv squared over r. All right, so the special thing in circular motion is the time it takes for one orbit. Do you guys remember what that is called? That's the period. They're calling it P here. We call it T. So this is the special time, and it's the time for a cycle, for a revolution, for an orbit. So I know that it goes all the way around the circle in this time. So my velocity is going to be the distance around the circle, which is the circumference, which is going to be 2 pi r over this special time. So I'm going to combine these two equations. I'm going to simplify just a little bit. And I'm going to say this cancels out and that cancels out. And we're going to say that we're going to plug in, I'll get rid of an r too. We're going to plug in 2 pi r over t for v. And so on this side, I still have gm over r. On this side, I'm going to have 4 pi squared r squared over t squared. All right, I'm going to get the r's to this side and the t's to that side. So over here, I'm going to have t squared gm, and over here, I'm going to have 4 pi squared r cubed. So looking at what we have, I'll move gm over here so we can match up with their equation. And I have, be helpful if I, so I have 4 pi squared r cubed. And so I'm going to have 4 pi squared over gm r cubed. Writing it below this one, I have that t squared is equal to 4 pi squared over gm, which is going to be a constant, right? If we're talking about the sun, 4 pi squared over a gravitational constant, the 6.67 times 10 to the negative 11th, and the mass of the sun isn't going to change, and that's going to be equal to r cubed. So what's the difference? Instead of having our radius of our uniform circular motion, we have substituted in a. So what is a? A is going to be our semi-major axis of orbit. So I'm going to go back 1 slide, 2 slides, 3 slides. And so that is going to be our distance from here to there is going to be A. And you can see how that's related to R, but we're only concerned about what would be the biggest R, because this R is changing, right? It's getting smaller, smaller, then bigger, bigger, then equaling that again. And so this works. And this led Newton to this idea. So what's important to us? What's important to us is that the period squared is directly proportional to the radius cubed, or the semi-major axis cubed if we're talking about ellipses, which they don't really have you talk about them. They'll ask you just general questions about ellipses. And the main thing to remember is that circular motion is special and ellipses are very common. So the moon is in an elliptical orbit around the Earth. We're in an elliptical orbit around the sun, but it almost looks circular. So we have this ratio from Kepler's third law. So if you know what the semi-major axis is, these are measured in astronomical units. That's the average distance between the Earth and the sun. You would know what the period is, because you know that p squared is related to a cubed. And so they're saying that a is 4, so I'm going to have 4 cubed is related to p squared. And this shows up in circular motion problems, especially in a multiple choice. And so you'd be able to find out what the period is. What makes the planets move like this way? You can see that it's opening up a door for Newton to explain this elliptical motion with a force. And Kepler thought it was a magnetic force, which he wasn't that far off. We still remember him because this made a big difference. The moving forward from us thinking that it's circles to ellipses led a lot to energy in the future, forces with Newton. This force at a distance from the sun, we could see that he's definitely a stepping stone. It bears reporting that this didn't work for Mercury. Mercury's orbit could not be completely explained with Newton's laws, with the universal law of gravitation, with Kepler's laws, and that opened up the opportunity for Einstein with relativity. So it added to the next one. You can see the building as we go through our understanding of what gravity does, and the idea now that gravity actually, masses will warp the space-time, and that's what causes the paths that things follow.